everybody is in a pressure cooker. We're all doing the best we can. We all need more grace for ourselves and for others. So, all righty, time to start. Looks like we're here. Just gonna wipe your faces off real quick. There, a lot of cat fur. Okay. So I have posted yesterday's Zoom video and then also some videos about calorimetry. So I don't know if you've looked at that. Let me share my screen real quick. Oops, let that person in. Okay, I think that you can see my screen now, right?
No.
Good, you got to keep me on track. How about now?
Yes.
Okay, good. So I'm going to click on calorimetry. And I'm going to let this person in. Okay, so enthalpy of fusion is a short video, and it's a classic experiment. It's an ice cube is put into warm water, and the ice cube melts and warms, and the warm water cools down. And a typical question would be, what's the final temperature? That's not what I'm doing in this video, but it's an important video because it's an important typical sort of problem in this chapter. The next one is a cold pack video that shows, you know, those cold packs that you're on the field and somebody twists their ankle. So you go and get one and you squeeze it till it pops and then you shake it and it gets super cold. There's an ammonium nitrate salt in there. And so what I did was I cut open the cold pack and I did another very typical calorimetry experiment with that cold pack in this video. And then experiment 8 procedure. If you haven't read the experiment, you need to do that because we're at the place in the semester where you don't want to fall behind. You're tired. It's just work. You just need to make a list and do the next thing. But you're probably going to want to watch that too. So all of these are about calorimetry. And then here are the notes for today. And then how to do the calculations for this experiment. Hopefully you've done the experiment before you join us tomorrow, or I will post that video soon. Are there any questions at this point? No. Okay. So now I want to show you a video on equilibrium. This is back when my husband did teach at Del Oro, and this is his arm. And there's an important science concept called dynamic equilibrium that you're probably familiar with. But here we go. So he has a pickle jar and he's got a ruler in one hand and he's adding water at a constant rate with the other. But there's a hole in the jar and so water is starting to leak out. So there's 2 processes that are opposite in direction going on. There's adding water and there's water leaving, water going in and water going out. But right now they're not happening at the same rate. And because they're not happening at the same rate, the height of the water in the pickle jar is going up. So at some point, the water leaving increases. Why is the water going out increasing?
Pressure.
What kind of pressure? So there's gas pressure pushing down, 1 atmosphere of pressure that we're all exposed to, and then there's the additional pressure of that weight of water. It's kind of like when you're a kid and you try to touch the bottom of the deep end of a swimming pool and your ears hurt a little bit. That extra pressure of the height of water adds to the atmospheric pressure you're used to. Eventually, the water fills. But you can see both of his hands. He's not changing the rate of water going in, but the rate of water going out increases. And when we get to the place where the rate in and the rate out are the same, we're at equilibrium. The height of the water isn't changing, but we know that things are moving in both directions all the time. So that idea is called dynamic equilibrium, and it's important because we're going to talk about how our thermometer works. So thermometers are important. Oh, dynamic equilibrium. The idea is the rate of the forward process and the rate of the reverse process. When those rates are the same, we're at equilibrium. So it could be water in and water out, and that's a physical process. So when you put a thermometer into a substance, and the fluid could be air or it could be a liquid, the level of the height of mercury changes until it doesn't change. And that's kind of like the water level on the previous example. The water level is going to go higher and higher and higher until it gets to a place where it's not changing. And when we get to the place where the height of the water isn't changing, equilibrium has been established. So what's happening here is, back in the old days, most thermometers were made of mercury. And mercury is super cool because mercury is a liquid at room temperature and pressure. Most metals would be solid, but it's not, it's a liquid. It's also good because it's a metal. And metals are really good at conducting heat. So here we have a liquid, something that can change shape, like it fits the shape of its container. And we have a metal, something that conducts heat well. And that's put into a sealed glass tube. And as the liquid gets warmer, the density gets less, it expands, it takes a larger volume. And it can move up and down depending on temperature. Okay, so the way they calibrate these is they put a thermometer into temperature like ice water. And so we have this long tube, and in ice water, they mark the height of the mercury as 0.0 degrees Celsius. And then they put it into boiling water, and they mark that line as 100 degrees Celsius. And then it becomes a metric scale, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Pretend those are equidistant. So then we now have the tens place, and we can break those down, and we have the ones place, and we have a thermometer. The way the thermometer operates is, if you put a thermometer into a warm liquid, so this is going to be like the before, equilibrium is established, and this is the after, equilibrium is established, which means this is where the height is not changing. Dynamic equilibrium. So what you can't see is, and the important concept this is based on is that the average kinetic energy is proportionate to temperature. If we're using an absolute scale, which is Kelvin. So if the kinetic energy goes up, the temperature goes up in a linear fashion, in a proportionate way. So initially we have mercury inside the bulb, and it's hitting the edges of the bulb or the thermometer. And each time I draw an arrow, the arrow is just showing energy, a molecule is moving or an atom is moving and hitting something. And if it's a long arrow, that means hitting with a great force. And if it's a short arrow, that means hitting with less force. And right now I'm just drawing a bunch of arrows inside the mercury saying there is movement, there's kinetic energy. Molecules are translating and rotating and vibrating and hitting things. When they do that, they transfer energy. Outside, there is also that same idea going on. I'm drawing a bunch of arrows. I don't care about the arrows that don't appear to be going anywhere. What I'm going to focus on are the arrows on the glass at the bulb. So there's kind of this push-a-war, tug-a-war, this energy game going on with the thermometer. Water is hitting the glass and mercury is hitting the glass. And if we aren't at a place where the hits toward the mercury and the hits toward the water are matched, there's a change occurring. When water was filling faster than water was leaving, there was a change occurring, and the change was the height of the water. But when we get to the place where energy has been transferred from this hot liquid to this mercury, and now they're at the same temperature, which is the same average kinetic energy, the hits in and hits out are equal. That's the dynamic part. There's still collisions happening where energy is being transferred, but they're matched. So that's dynamic, and matched is equilibrium. And the height of the water or the height of the mercury stops changing. Another really cool thing about mercury is that it has a very low specific heat. Oops, don't like this pen. Hang on. Okay, and this is an idea I'm going to talk about next that is important in this chapter. But the basic idea is when it gets energy, it expresses that energy as kinetic energy, which means the temperature changes. The height of the thermometer goes up. If it had a high specific heat, that means some of the energy coming in would be saved as potential energy. So, and I'm going to talk about that more in a second, and it's important. So what that means here is when I put the cold thermometer in the hot liquid, and we go from the place of not at equilibrium to at equilibrium, very little energy has left the water and gone to the thermometer. But the thermometer stops moving because the average kinetic energy is the same, and then we measure it and we can read the temperature. So the important ideas here, if you can't appreciate the beauty of a mercury thermometer, that's okay, but it's pretty amazing. But the important thing here is when the thermometer stops changing temperature, it's because the kinetic energy inside is equal to the kinetic energy outside. There's no net flow of kinetic energy, just like that pickle jar. Okay, so now I want to talk about what specific heat is briefly. And of course, at any point, if you have questions, I hope you'll ask. Okay, so water is pretty amazing. Ignore this for a second. So there's two pictures I have in my mind, and one is going to be near a lake, and the other is going to be in the desert. So all day long, the sun is shining and sending energy through radiant energy to both environments. But near a lake, well, at a lake, we have a lot of water. And so that energy is being transferred to the air and to the water. And in the desert, we have a lot of sand. So that energy is being transferred to the sand and to the air around it. In the day, which one is hotter? In the night, which one is colder?
Desert for both.
Yeah, aren't they both environments getting the same sunshine? Why is the desert hotter in the day and colder at night? And the answer is, it doesn't have sand, doesn't have much capacity to hold heat. And so all the heat it gets from the sun during the day is becoming kinetic energy. And kinetic energy is directly related to temperature. So as that energy comes in and becomes energy of movement, the thermometer goes up. Now, the water is going to take some of that heat and make it kinetic energy, but it's also going to take some of that heat and store it as potential energy. And so the total energy from the sun for water goes kind of half and half. Half to potential, it's stored, it's saved for later. If we need more energy, we have it later. But for the total energy for the desert, you know, there's a little tiny bit of potential energy, but mostly it's kinetic energy. As soon as the sun goes out, as soon as it's nighttime, there's no stored kinetic energy. And if the kinetic energy is low, it gets very cold because kinetic energy and temperature are related. But for the lake, when the sun goes out at night, even though there's no more total energy coming in from the sun, oops, didn't mean to do that. There is some stored energy stored in the water because water is good at storing energy. It goes back into the environment. And that stored energy keeps the temperature temperate. So during a large body of water, the hots aren't as hot and the colds aren't as cold because water is acting as this huge heat source that can absorb heat without the outside temperature changing much during the day, and then release heat without the outside temperature changing too much at night. So it has to do with this idea that heat comes in and some of it is stored as potential energy to be used later, and some of it is immediately used in the form of movement, kinetic energy. And we can measure kinetic energy with a thermometer. Okay, so there is a super important equation in this chapter that looks like this: Q equals mc delta T. Q is just the heat coming in, like maybe the heat from a sun, so heat transferred. And when that heat is transferred, it is shared. So this is just mass in units of grams. The heat is shared among all the molecules. And if you have a bunch of sand molecules, they share all the energy. And if you have a bunch of water molecules, they share all the energy. But then what they do with that energy is different. For water, it has a high specific heat. So C stands for specific heat, and specific heat is a potential energy idea. And then the change in temperature is related to kinetic energy. Sand isn't good at storing energy. So when the energy comes in, it's shared among the different molecules, and then it goes to kinetic energy, which means the temperature goes up. Water is very good at storing energy. It has a high specific heat. And so when the energy comes in, when Q is transferred, some of it goes to potential and some goes to kinetic. The kinetic energy increase causes the temperature to go up. The potential energy increase is hidden. It's the capacity to do work, but work isn't being done until it needs to be done. When does it need to be done? At nighttime, when there's no more heat going in. Water has a specific heat. So this is liquid water of 4.184 joules per gram degree C, some derived units, which is the same as 1 calorie per gram degree C. This is a value that you need to have handy because when you're given problems, you won't be given this value. You're expected to know it. I remember taking a test to get into my master's program in chemistry. And one of the questions required that I know the specific heat. And I thought, am I supposed to know that? Yes. Do you know the boiling point of water? 100 degrees Celsius. You need to know that. Do you know the freezing point of water? 0 degrees Celsius. You also need the specific heat for liquid water. Okay, so the first two problems are just, we're going to solve for one of the variables. There's 4 variables, you've been given 3. If 80 grams of water, so I know the mass, at 75 degrees Celsius cools to 25, so that's a delta T, how much energy has been released? Energy is Q, we're solving for Q. And then you're told the specific heat of water, but normally you won't be. Other substances you'd be told, but not usually water. Okay, so I'm solving for Q. How much energy? Okay, delta T is final, 25 degrees Celsius, minus initial, 75 degrees Celsius. So it's going to be a negative number. And when I do a delta T, sometimes we lose digits. Here we're not going to, because 75 from 25 is negative 50, and we still have the ones place. But you need to keep track of it, because sometimes you lose a sig fig there. I got 4,000, and let's check our units. Grams cancel, degrees Celsius cancels, we're left with calories. lowercase c. So I had 3 sig figs, 3 sig figs, 2 sig figs. I can either change it to kilocalories or capital C calories, or I can use scientific notation. Questions? Alrighty, the next one, similar problem, but here we're solving, and the math's a little harder. What will the final temperature be? Just remember that delta T is final minus initial, and we're solving for T final.
I have a question on the previous one.
Sure.
Why, if the answer we get is negative, why is the answer not negative?
Oh, it is negative. Thank you.
Oh, thank you.
Yes, okay. Thank you. And negative means exothermic. Thank you for correcting me. Which means heat was released. And that makes sense. If hot water cools, that heat went somewhere. Other questions? Okay, so when heat is transferred, Q, that heat is shared among the mass, and then the heat goes toward, if heat's coming in, it raises potential energy, C, it's stored, and it raises the temperature, kinetic energy. That is usually true, Q equals MC delta T. But there are times when all the energy that goes in increases potential energy, and that's when there are phase changes. So I want to show you a phase diagram that I had on a previous video that you may have seen already. And I'm going to do the phase diagram for water at first because water is familiar, but just keep in mind that anything that can be solid, liquid, or gas can have its own phase diagram. So this is the general idea, and we're starting with water because it's familiar. And this phase diagram is at constant pressure. Which means there will be a time when the pressure can change, but not in this class. That's Chem 1B, and a little bit in 3B. Okay, the first thing is, on the bottom, we're gonna write Q and draw an arrow to the right saying, as we put energy in, what happens as we go to the right? And then at constant pressure, what's gonna happen is the temperature may change. So if we have solid ice, solid water, we put energy in and the temperature goes up. Until we get to the place where there's a phase change, where we're at 0 degrees ice. And then all the energy going in is just separating these polar molecules. And so it's all going into increasing potential energy. There's no kinetic energy change. So when you melt ice, the temperature stays the same until all the ice is melted. Then, once all the water at 0 degrees Celsius has changed from solid to liquid, now adding more energy goes into raising the potential energy and the kinetic energy. This line here is ice warming. And Q equals MC delta T. And this C is the specific heat for solid water, which is not 4.184 joules per gram degree C. It's a different number. It's not a number you need to memorize. Once all the ice has warmed, all the energy going in is simply causing a phase change. So right here, we have solid at 0 degrees C. And right here, we have liquid at 0 degrees C. So all the energy going in, there was no temperature change, no kinetic energy change. There's a different equation, m delta H. And the delta H stands for the change in enthalpy, which we'll talk about today. And because this phase change is called fusion, which is melting, we put a F here. Then, as energy goes in, the liquid water warms. Q equals mc delta T. The energy goes in and is shared among the molecules. Some of it increases the potential energy, C, 4.184 joules per gram degree C. And some of it goes toward increasing kinetic energy. Okay, when we get to the place where, for water at 100 degrees Celsius, let me find a new color. When we get to the place where the water is 100 degrees Celsius liquid, and then it's becoming 100 degrees Celsius gas, all the energy going in is increasing potential energy. That's a phase change. So this is another phase change. And whenever there's a phase change, it's m delta H. All the energy going in is shared and then increases potential energy, delta H. Because that phase change, liquid to gas, is called vaporization, we put a V down here. I ran out of room, but there is one more line we could draw, and that is just the gas getting warmer. So I'm going to pretend with, I don't know, this orangey color, that I've got a line going up. And that phase change, that is gas forming. And so the energy going in, Q, is being shared, M. Some of it's being stored as potential energy, C, but the C is different than the specific heat, the C that we had for a solid and that we have for liquid, and then delta T. Okay, so there's a pattern here. If there's temperature change, Q equals mc delta T. If there's a phase change, Q equals m delta H. Each of those C's and each of those H's have a different physical value. The only one you're expected to know is the C for liquid water, but all the other ones you would be given. Everything that we've done so far was going to the right on this diagram, and those are all endothermic processes. If we were going the other direction, that would be exothermic, and there would be a negative sign to indicate that. And we'll do a couple problems so you'll get to see that. Okay, so are there any questions on this diagram before I erase it? Okay, so every time you're given a problem that isn't calorimetry, it's just heat being put in, it's called a phase change idea. You're going to start with this diagram, where we're adding energy, and we're starting with a solid warming, solid melting, liquid warming, liquid vaporizing, vapor warming. And then the temperature that you put here is going to be whatever the normal melting point or freezing point is for that substance. If it's water, it's 0 Celsius, but if it's not water, it's something else that you'll be told. And what we put here is going to be the boiling point. There's a peacock looking in the window at me. It's very weird. And the boiling point for liquid water is 100 degrees Celsius. But if it's not water, then you're going to need to be told what it is. Every time we have a line with a slope, Q equals mc delta T. Oops. What is C? You'll have to look it up because it depends on the substance and the phase of the substance. I don't know if you can see it. Can you see that guy?
That's cute.
doing there?
Is it yours?
No. Ridiculous. Okay. And then every time that there isn't a slope, so this is slope equals 0. Those are horizontal lines. Q equals m delta H. And which H it is depends on is this fusion or vaporization. And finally, there's going to be a third Q, which is Q equals C delta T. And this is for bomb calorimetry, which we'll touch on today. These two are used for coffee cup calorimetry. And the difference between these is coffee cup is at constant pressure. So it uses that diagram we were just looking at. And bomb calorimetry is constant volume. We'll talk about it later. It doesn't use this diagram. Okay, so what does Q stand for? Heat transferred. If Q is positive, that process is endothermic. Heat is being put in. If Q is negative, that process is exothermic. Heat is coming out. Every time we're going to the right here, that's endothermic. Anytime we're going to the left down this diagram, that is exothermic. If it's exothermic during a temperature change, it will show final minus initial will give you a negative number. If we're headed to the left, but we're doing a phase change, we have to put the negative sign in to make it work. Okay, so I'm just going to make up a problem, and I have information for 3 things: water, acetic acid, and ethanol. So let's just do ethanol. I'm going to say we have a 15-gram sample. The way of abbreviating ethanol is ETOH, and the T is lowercase, but everything else is capital. And I want the ethanol to go from, let's see, maybe 50 degrees Celsius to 100 degrees Celsius. So what you're going to do is figure out how much energy is required to go from 50 degrees to 100 degrees. What we need to know is where are we on that phase diagram. So I'm going to draw a little phase diagram here. And solid warming, solid melting, liquid warming, liquid vaporizing, vapor warming. So the number I put here is the melting point. And for ethanol, the melting point is negative 117 degrees C. And the number I put here is for boiling, and for ethanol, the boiling point is 78 degrees C. So I have temperature on my Y and heat being put in on my X, and I figure out where we are. And we're at 50, and 50 is below 78, but more than 117. So I'm just going to randomly pick something between those two numbers and say that's 50. So we have a liquid at 50 degrees C. And then we're headed to 100 degrees C, which is more than 78. So we have a warm gas. So I now know that I have to warm a liquid, vaporize a liquid, and then warm a gas. I have 3 Qs that I'm going to add together for the total heat transferred. For this Q, I'm going to call this Q1, this is Q2, and this will be Q3. For Q1 and Q3, it's MC delta T. The things that will be different are which C do I use, and then what is delta T, final minus initial. For Q2, it's going to be M delta H, but I need to pick the right delta H, the one that has to do with vaporizing. Okay, so delta H for vaporization is here, and it's in units of kilojoules per mole, but I'm starting with grams, so I'm going to have to do some changes there. Okay, so I'm going to start out with my Q1 equals MC delta T. And my mass is 15 grams. The C is for the liquid, which is 2.3 joules per gram degree C. And my delta T is final, 78, minus initial, 50. And I'll get a number. For Q2, which is the phase change, it's just M delta H for vaporization. So 15 grams. The enthalpy of vaporization is 38.56 kilojoules per mole. So I'm going to write kilo as 1,000. And then I'm going to have to convert my grams to moles or my units aren't going to cancel properly. For Q3, M is the same, but C is different because now we're talking about the gas phase. So it's 0.95 joules per gram degree C. Once I have those values, I add them together and check my sig figs and report that answer correctly rounded and with units. Oh, you don't know. Oh, you do have the formula for ethanol. C3CH2OH. So there's 2 C's, 6 H's, and 1 O. I came up with 13.9 kilojoules. Did you get that too? Did anybody get that?
Wait, so I have one question on Q2.
Mm-hmm.
Where'd you get the 38.58?
Right here. It's the enthalpy of vaporization for ethanol.
So shouldn't that be 38.56?
It should be. You're right. Ah, shoot. Okay, let me try it again. Thank you, James.
Yep.
Okay, that just changed this to a 2. So I don't think that changes my final answer. Did anybody else get that final answer?
I'm lost on what you're doing to get that final answer.
Oh, I'm saying the total amount of energy I had to put in is Q1, 996 joules, plus Q2, 12,552, plus Q3, which is 313.5 joules. I'm adding all those individual Qs together. Okay, for the next problem, we're going to use the same table, but this time let's do acetic acid and have it cool from 125 to 75 degrees C. When I do this, I would still have it go solid warming, solid melting, liquid warming, liquid vaporizing, gas raising in temperature. I still draw it the same way, but in my head, I'm thinking we're going down, becoming a solid, and then going down. So I'm going to put in the melting points and the boiling point. And I see that I'm starting at 125, which is above the boiling point, and cooling to the boiling point. That's Q1. And then we're going to have the hot gas at the same temperature become hot liquid. That's Q2. And gas to liquid is vaporization, so I put a V there, and I grab the value that has a V. Oops, that's the wrong one. And I grab the value that has the vape. And then finally, we're cooling from its boiling point to the final temperature, which we said was 75. That's going to be Q3, MC delta T. Does the roadmap make sense? So the delta T's, because final is lower than initial, final is 75 or 118, and initial is 125 for Q1. The delta T is going to be negative. So the Q is negative, which makes sense because cooling is an exothermic process. Heat is being dumped. But for the second one, this Q2, when I use delta H for vaporization, I need to change it to a delta H for condensation, which is the same number, 23.7 kilojoules per mole, but it's an opposite sign because condensing is exothermic. So for all three of these Qs, the sign will be negative. For the ones that have a delta T, it works out naturally, final minus initial. For the one that has a delta H, you have to put the negative in, reminding yourself, if it took energy to vaporize, that's positive. Energy is released when the opposite process happens, when condensation happens. Okay, I'm going to try to squeeze all of this on the same page, and you can do the same. Oh, I didn't give you a number of grams. How about we just do 20 grams to 2 sig figs. Okay, there are two problems like this on your thermochem assignment this week. I think one is probably you're putting energy in, so you'll get a positive value plus a positive value plus a positive value. And the other one is probably exothermic, energy's coming out. So negative, negative, and then for the phase change, you have to apply the negative. You have to put that sign in. Because you're taking an enthalpy for vaporization and changing it to condensation, which is the opposite process. And then the main thing is when you are given a range, like 125 to 75 degrees C, you have to know where the boiling and melting points are to know where you are on that phase diagram. This can't be done in one step if there's a phase change involved. Okay, so to summarize and then to move on. Where did I put it? Somewhere here there are three equations. There they are. And for coffee cup calorimetry, which means the calorimetry that we're doing for experiment 8, and that is typical in our class, it's a constant pressure. Those are the two equations. This is if the temperature is changing, and this is if we have a phase change going on. For the third kind, which is bomb calorimetry, everything is included in the calorimeter constant for the bomb calorimeter, and you're just multiplying it by the temperature change. So we're going to start with coffee cup because that's what we're doing mostly. Heat comes and heat goes. In the previous two examples, we were either putting heat in to raise the temperature and change a phase, or drawing heat out to lower the temperature or change a phase. But usually we come to thermal equilibrium. So for calorimetry, bomb calorimetry or coffee cup calorimetry, we're using this idea. If this is losing heat, the surroundings are gaining, and vice versa. How much? We need it all to add to 0. So there's a conservation of energy argument. So in a coffee cup calorimeter, we typically have these three ideas. We can have a reaction happening in solution. Or we can have a solid dissolving. In Chem 3B, you'll do it with a reaction. And in my example video of a cold pack, I'm doing a dissolving. For these, you're going to solve for Q. And so for the Q, the reaction, I'd put an RX in. And for Q of dissolving, I just put Q of the salt. And then you divide it by the number of grams or moles to come up with an enthalpy of reaction or an enthalpy of dissolving. So that's one kind of problem you might see. Another kind of problem you might see is hot metal in cold water. And that's the lab that we're doing this week. So those are the ones I want to focus on more. But there is an example of this one in a video that I have put on the page. And then the third kind would be, I have a coffee cup calorimeter, I have hot water, and then I'm going to put an ice cube in there and see what the enthalpy of the ice cube melting fusion is. And for this one also, I made a video and I put it on the page. So right now I want to focus on the one that's like the lab that I don't have a video of, except to explain how to do the lab. Okay, so if you put a hot metal into cold water, we're going to start with this idea. No energy is lost. The metal is going to dump energy and the water is going to receive the energy. When the metal dumps energy, that's an exothermic process, so I'm going to let it be red, and I'm going to say Q equals MC delta T. the mass of the metal, the specific heat of the metal, and the change of temperature of the metal. Where is all that heat going to go? It's going to be received by the cold water. So I'm going to let it be blue for endothermic for cold, MC delta T. W's for water. And all of this is going to add to no heat is lost. Heat just comes and goes. So I'm reading my problem, and I see that I have a mass for the metal, an initial temperature for the metal. I have a mass for the water. Oh, unknown mass, I lie. I'm going to find the mass of the water, but I have an initial temperature for the water, and then I have a final temperature for both. We're told what the specific heat of the water is. I'm sorry, we're told what the specific heat of the metal is, and we just need to know what the specific heat of the water is. It's liquid, so it's 4.184 joules per gram degree C. Alrighty, so it looks like I'm solving for this. I can rearrange and then plug things in, or I can plug things in and then rearrange. It's easier to rearrange first because we don't have all those units in the way. So I'm going to go ahead and subtract MC delta T from both sides. And then divide by C and delta T for the water. To solve for M. Oh my gosh, I just realized my colors are backwards because it was hot water, cold metal. I'm so sorry about that. Did anybody else get that answer? I got 39 grams.
I got that as well.
Okay. 2 sig figs?
Yes.
Okay. Yeah, the 2 sig figs that Michelle and I got were because when we subtracted this to get a delta T, we lost the tens place.
Wouldn't that be negative? Wouldn't it be negative 3.3?
It was, and then I said this was negative and that was negative. Let me let them both be positive.
Okay, thank you.
Okay, here's another one. This time the question asks for what is the specific heat of zinc? So we're trying to find what C for zinc is. The process is all the same. This time it is a hot block of metal, like your lab. I have a class. What's up, babe? Okay, have fun. Questions?
Would this one be a negative answer because of the negative 73.8?
No, because when I moved this term to the other side, it became negative. I guess the negative's there.
Okay.
Yeah, I didn't show that. I should have shown it right here. Also, specific heats are always positive. So if it was negative, I'd have to go back and check. What I had done wrong, which you pointed out. Thank you. Okay, I have another example, but we're not going to have time to do it. Oh, 2 more examples. I think that I'll have to talk about bomb calorimetry and this last idea, enthalpy and energy, which is we're dissolving a salt, in this case a base. I'll have to do those in a separate video, and then I'll just post it somewhere on this calorimetry page, but we've already gone more than an hour. I want to point out, when you do your coffee cup calorimeter problems, which is hot metal and cold water. So right now I'm just talking about the lab you're going to do, experiment 8. We're still making this idea that the hot metal is going to dump heat, and where's it going to go? It's going to go to the water. But some of it gets lost to the calorimeter. So in part 2, you're going to be figuring out what your calorimeter constant is. And here, Q equals C delta T. So you're solving for, I think they call it B delta T. You're solving for what B is, which is a calorimeter constant. It's just a little bit of waste that happens because we're doing this in our kitchen with equipment that's made out of, coffee cups. So you have to solve for that in part 2. And then once you know what that is, in part 3, you're going to use it with your metal and some hot water, cold water. So the difference in the lab is where problems are a little bit more like real life, where even though we assume all the heat is transferred, none is lost. In real life, some of it is transferred to waste. It's lost to the room, the coffee cup. So for the lab, we have this extra part, which is figuring out how leaky, energy-wise, our coffee cup is. But whenever we have lecture problems, we're going to be making an assumption that's a good assumption. And that is no heat is lost to the surroundings. So there's no coffee cup calorimeter constant that has to be considered for a problem that's in lecture. In lab, which is real life, we have to consider that because it's real.